September 7, 1941, America woke up to fire. 3 days later, another crisis hit quiet, soaking, relentless, tents rotted, supplies drowned. Men got sick before they ever saw a battlefield. What do you build when you have no lumber, no carpenters, and no time? A wall fights the wind and loses. A curve invites the wind to slide and wins. In 60 days, a small team turned corrugated steel into shelters that beat storms, bombs, and jungle heat. Not blueprints, not someday. A kit you could ship by rail, drop on a beach, and bolt together with a wrench. Imagine the brief. Lighter than a Jeep. One day to
We'll
assemble,
need to adjust the
no
propulsion
foundation,
system here.
under $1,000
Yes, that's
during
what I was
wartime,
thinking.
and it had to survive typhoons, monsoons, and blast shock. So how do you mass-produce survival? You stop thinking like a builder and start thinking like an engineer on a deadline. You borrow the arch, you rib the steel, you turn a roof and walls into one continuous structure, every panel sharing the load with its neighbor, every 6 inches locked by a bolt. Ship
Move
it
them
flat.
up now, quickly!
Nest the panels like bowls. Land it anywhere from coral to permafrost. This is the story of the Quonset Hut. Why a curve changed the math of war, and why that curve still matters when the sky turns black. The enemy wasn't just across the water. In the Pacific, the enemy was the sky. 2 to 3 weeks after a Marine unit pitched its tents, canvas rotted into rags. The seams bled rain. Floors turned to broth. Rifles, boots, bandages, everything took on the sweet, sour smell of mildew. Supply depots flooded. Ammunition swelled and failed. Men coughed themselves awake at 0300, hacking in wet air that felt more like bathwater than atmosphere. The medical corps logged the pattern. Chest infections spiking, pneumonia cases rising, duty rosters thinning. Not because of bullets, because of weather. Meanwhile, the War Department's morning briefings grew grim. Commanders radioed in from coral atolls with the same plea. We can land the men and the fuel, but we can't keep either dry. Try building wooden barracks. In theory, that solves the problem. In practice, it's a fantasy. On a low ring of coral in the middle of nowhere, there is no timber stand, no lumber yard, no skilled carpenters just waiting around. Every stick of wood must be shipped over submarine-hunted water. Every hour of skilled labor must be siphoned off a war that needs mechanics, gunners, and pilots. Traditional barracks take weeks, require tools and trades you don't have, and demand foundations you can't pour in a monsoon. So the question hardens. What can you build fast, with tired hands, in the wrong weather, on the wrong ground? There was a clue, an idea born on a different front, in a different war. In 1916, a Canadian engineer named Peter Nissen drew a half-cylinder and wrapped it in corrugated iron. The Nissen Hut. It wasn't pretty, but it was brilliant. A semicircle laughs at wind. Corrugations stiffen thin metal the way a fold stiffens paper. For the British in North Africa, they were a godsend, fast to assemble, stubborn in sandstorms, indifferent to aesthetics. But what works in Libya can fail in Luzon. The classic Nissen used heavy steel panels and an internal frame, a skeleton you had to build before you could skin it. It wanted concrete footings or carefully laid timber sills. That's weight, that's time. And the ventilation that felt fine under a dry Sahara sun turned the interior into a steam bath in jungle humidity. The geometry was right, the system wasn't. So the Navy wrote a brief that sounded like science fiction and then stapled it to reality. It had to fit on a single rail car. It had to assemble in one day with basic hand tools, by people who might never have built anything more complex than a camp stove. It had to need no foundation, sit on coral, dirt, or sand without cracking, heaving, or rotting. It had to survive monsoons, typhoons, and blast shock. And it had to hit a wartime cost target under $1,000 in materials, so you could buy not just one, but 10,000. The word impossible didn't appear on the page, but everyone could read it between the lines. The Navy didn't go to an architect's studio. It went to a place built to move metal. Quonset Point Naval Air Station on Narragansett Bay, Rhode Island, 1941. A windswept strip of shoreline with railheads, cranes, and workshops that smelled of cutting oil and salt. From here, the Bureau of Yards and Docks kicked off a crash program. Design, prototype, ship. They tapped the George A. Fuller Company builders with a reputation for getting steel where it needed to go. Fuller signed on, rolled up sleeves, and within 60 days turned a contract into the first production huts. 60 days, from spec sheet to shelter. That schedule only made sense if you stopped thinking like a builder and started thinking like a manufacturer. Buildings are unique. Products are standardized. A building forgives improvisation. A product demands repeatability. The Navy needed repeatability at scale. Enter
Our
a different
vision for
kind of
tomorrow
influence.
is not just
an
a
American
dream,
futurist
but a
talking
blueprint
about
for a
houses
brighter,
the way
more
Detroit
efficient
talked about
future
cars.
for all.
Buckminster Fuller's Dymaxion ideas were
We need to move these
controversial,
panels to
even
shipping
mocked,
immediately.
but the core
Confirmed.
insight was pure
Assembly
oxygen
is waiting
in
on
a
our
war.
go-ahead.
Treat shelter as an industrial
The quality
product.
control
Stamp,
here is
number,
second to none.
ship, assemble. Use the supply chain you have, not the craft knowledge you don't. This wasn't about adopting someone's philosophy, whole cloth. It was about combining that product mindset with the Navy's own systems, engineering requirements, trade-offs, tests, and with heavy industry partners who knew steel down to the mill scale. The core team looked less like a design studio and more like a strike force. On the engineering side, Peter De Jong, practical, relentless, the kind of engineer who starts with the wrench in his head and works backward to the drawing. On the architecture side, Otto Brandenburger, trained to think in spans and skin, skeptical of dead weight, obsessed with getting volume out of geometry rather than material. On the industrial side, Strand Steel, a division of Great Lakes Steel, the people who could corrugate miles of sheet, hot dip it in zinc, and deliver it by the trainload. And on the ground, the Seabees, the Navy's construction battalions, tough, ingenious, allergic to excuses who would turn kits into shelter on beaches from Guadalcanal to Adak. Each actor had a role. Together, they had a shot. Start with constraints, not dreams. The ground is coral. It's sharp, porous, and unforgiving. You can't pour acres of concrete on short notice, and when the tide comes in sideways, it will search for any weakness. The air is wet and salty. Anything that can rust will, and faster than you think. The workforce is whoever stepped off the landing craft yesterday. Tools are basic. Time is the only thing you have less of than dry socks. Given that reality, the impossible spec reads like common sense. No foundation? Good, skip the step that drains days and cement. 1 day to assemble? Good because 2 days invites a storm. Fit a rail car? Good because if it doesn't ride a train, it's not getting to the port. Under $1,000? Brutal, but it forces you to cut everything that doesn't make it stand in wind or keep out rain. What about weight? Lighter than a Jeep isn't poetry, it's logistics. 4 men have to lift a panel. 6 or 10 men have to raise a bay. A crane is a luxury. Your rigging is a rope and a prayer. The British Nissen gave them the arch, and the arch gave them physics. Curves shed pressure. In a gale, a flat wall feels the full punch. A curve turns a punch into a glancing blow. But the team wasn't going to copy the Nissen skeleton. Tropical termites make sawdust of wood. Bolted frames loosen with vibration and heat cycles. Add weight, and you add shipping. Add complexity, and you add failure points. So the early decision radical for 1941 was to let the skin carry the loads. No internal wooden frame. A self-supporting shell of corrugated steel, each ridge acting like a miniature I-beam. Bolt every panel to its neighbor every 6 inches, all the way down the length, and the building stops being parts. It becomes one structure, a compression ring, a continuous arch that can flex and return, rather than crack and collapse. Of course, none of that meant anything if you couldn't ship it right. The flat pack problem dominated the brief. 96 curved panels nest like bowls, shrinking 8 feet of stacked steel down to 14 inches of kit height. End walls and frames go flat. Hardware goes into a single crate with illustrated instructions that don't care what language you learned first. 1 railcar holds 1 hut. 1 ship holds 200. That's not a design flourish. That's the supply chain doing math at scale. And the math only works if the field assembly does. The Seabees would later formalize it into an SOP, 6 to 10 men, 1 day. No welding, no concrete. But in Act 1 of this story, that's still a goal, not a guarantee. The planners knew it. Every hour saved in design becomes a day saved in theater. There's another constraint, hidden in plain sight: cost. You can't armor your way out of a typhoon. You can't gold plate 1 million square feet of roof. Wartime budgets are big, but they aren't infinite, and steel, zinc, and shipping compete with ships, guns, and planes. The under $1,000 target is less about an exact price and more about discipline. Galvanize where it matters, not where it flatters. Add vents where condensation kills, not where comfort merely complains. Choose a radius that gives headroom without wasting steel. So Act I ends not with a design, but with a mindset. A building as a bill of materials, an assembly line as an army, the beach as a factory floor. The Navy's impossible brief is still impossible if you think like a traditional builder. If you think like a product engineer under fire, it becomes a list of solvable problems, each with a test you can run tomorrow. Set the stakes. Men are getting sick, supplies are soaking, the monsoon doesn't care about your schedule. Across the ocean, U-boats don't care about your cargo. You either ship a shelter that works, or you ship another problem. At Quonset Point, in late 1941, the clock started. Fuller's team reached for steel. Budok's wrote the specs and sharpened the pencils. Strand steel lined up coils and zinc. The Seabees sharpened wrenches. The question wasn't, can we build a perfect building? It was, can we build the right kit fast enough that a kid with a wrench can make it stand today? From here on, this isn't architecture, it's logistics powered by physics. The arch will carry the wind, the corrugation will carry the span, the bolts will carry the neighbors, and the system will carry the war's most precious commodity, time. Next, how a 60-day sprint turns a sketch into steel, and why the first prototype taught them what to keep, what to cut, and what to corrugate. Here's how you build a building in wartime and why this one behaved more like a product. The clock started at 60 days, not for drawings, for a pipeline. Mornings began with quick pencil sketches, no cathedral renderings, just sections, joint details, bolt patterns. By afternoon, the shop cut and bent metal. At night, they tested, torque a bolt to failure, load a span until it bows, hose seams until water finds a path. Dawn brought revisions taped over revisions, version B folded into version C before lunch. That rhythm sketch, fabricate, test, revise, turns opinion into evidence. It also forced the first big decision. Decision number 1, no internal wood frame. In the tropics, termites don't nibble, they erase. Any frame you built, you'd have to protect, inspect, and rebuild precisely the kind of maintenance a forward base cannot spare. So De Jong and Brandenburger flipped the logic. Let the skin carry the loads. Corrugated steel, thin, light, and strong, once it's folded, would be both roof and ribs. Join it edge to edge. Spread the load across the shell. Fewer parts, fewer tools, fewer failure modes. The second big decision shrank time and weight in one stroke. Lose the floor from the base kit. Every early prototype with a packaged wood floor blew the schedule. It took too long, soaked up too much volume, and rotted first. The engineers cut it. You could always lay sleepers later, pour a slab if you had time, or drop a raised floor for clinics and offices. But the baseline shelter, weather, wind, and walls had to stand without it. The delete shaved about 1,200 pounds from the shipment and took assembly time for the shell down toward 8 hours under drill conditions. Those decisions clicked because the team treated each part like a part number, not a custom detail. Panels got stamped and nested. End walls were standardized openings, 1 door, 2 windows with options you could swap. Fasteners lived in a single crate, and every time a test broke something, the break became data. Edge buckling? Increase corrugation depth. Leak at the seam? Add a stiffer lap and a better washer. Wrench clearance too tight for gloves? Move the bolt line ½ an inch. Product thinking means your mistakes travel back up the line and make the next kit better fast. A flat wall fights the wind and loses. A curve invites the wind to slide and wins. Those ridges on the steel? They turn thin metal into a row of tiny I-beams. Bolt every panel to the next, every 6 inches, and the whole roof becomes a compression ring. Graphic 1. Wind versus shape. When air hits a flat wall, pressure spikes and vortices rip at edges. That's why roofs peel off and walls rack. A semicircle bleeds those pressures away. Flow accelerates over the crown. Pressure drops, and the load stays attached instead of tearing seams apart. Aerodynamics aren't just for wings, they're for roofs that don't want to fly. Graphic 2. Stiffness from shape. Take a thin sheet, load it. It sags like laundry on a line. Now crease it into ribs, corrugations, and each rib acts like the web and flanges of a miniature I-beam. Moment of inertia rises. Deflection falls. You've bought stiffness with geometry, not mass. That's how you ship strength thin. If you stitch the shell with bolts every 6 inches, end to end the panels stop acting like strangers. Loads spread along the hoop, not down isolated studs. Wind tries to lift. The ring ties everything together and hands the tension to the anchors in the ground. That's why a Quonset isn't a roof sitting on walls. It is the wall. It is the roof. It's one continuous structure. Hurricanes hate continuity. Size wasn't a style choice. It was math with blisters. The original Navy pattern ran 16 by 36 feet with an 8-foot radius compact, rail-friendly and fast to skin. As the program scaled, a standard 20 by 48, about 960 square feet emerged as the sweet spot, big enough for 30-plus bunks or an aid station. Small enough that 4 men could handle a panel without a crane. When you needed volume, the 40 by 1 to 100 warehouse variant delivered clear span space for pallets, parts, and bread ovens. Why those numbers? Because railroads and hands set the limits. 16 feet keeps you inside standard width. 48 folds into 3 bays you can raise in sequence. The radius gives 7 feet of headroom at the haunch without wasting steel. And none of it requires an internal frame. Geometry did the lifting so men didn't have to. Then the tropics taught a lesson paper can't. In Panama, inside temperatures swung with the Sunday night fell, steel cooled, and humid air kissed the underside of the roof.
The condensation is causing structural
rain,
damage.
Indoors, drips off the crown, puddles on footlockers. You don't negotiate with condensation, you vent it. So the kit grew smarter. End wall louvers, big ones, moved hot air without inviting driven rain. A ridge vent relieved the highest, wettest air where it wanted to collect. The bill of materials climbed about $47 for the extra metal and labor, but the trade was sanity. Sleep without a shower, doctors without a drip, dry wiring, fewer mold blooms. Venting was a system choice, not an afterthought. Louvers sit where the shell stays strong. The ridge vent opens a slit along the compression path without breaking it, because the load travels around the opening, not through it. That's another product truth. Every comfort feature must earn its keep structurally. Anchorage, the quiet hero, closed the loop between physics and dirt. You needed options because ground means 3 different things in the Pacific: sand that flows, coral that chips, and hardpan that laughs at stakes. On sand or loam, think tents scaled up. Steel stakes bite deep. Galvanized guy cables tie the base plates to the earth. Tension is your friend. Tight lines preload the shell so gusts spend their energy moving air, not your roof. On coral or uneven fill, you drop sleepers, timber sills, or steel channels that spread loads and give you a level line. Bolt the base to the sleeper. Let the sleeper pick its way over the rock. You gain speed and tolerance without hauling a batch plant to the beach. On hard ground or airfield margins, PSP pierced steel planking does double duty. It's runway by day and foundation by afternoon. Lay it, line it, bolt through. The shell doesn't care if the ground was poured or placed. It cares that the anchors have something to pull against. Anchoring turned out to be the line between survived and rolled like a barrel. The arch carries the wind, the ring carries the load, the anchors carry the ring. Miss any link and the storm will find it. Get all 3 right and typhoons turn into loud nights you can work through. By the end of the 60-day sprint, the kit behaved like a sentence with few, strong words. 96 panels, each light enough to handle in pairs. End walls pre-cut to standard door and window patterns you could mirror for cross-ventilation. A single crate of hardware with bolts, nuts, and washers that liked salt as little as you did galvanized, not painted. An instruction booklet designed to be read by pictures first and English second. Most importantly, everything nested. The steel that gave you curve also gave you packing density. Stack the ribs like bowls, and 8 feet of metal shrinks to a 14-inch bundle. That's how one railcar becomes one building. That's how one Liberty ship becomes 200 roofs. That's how numbers turn into shelter. The product mindset also guarded against the enemy you don't see in blueprints: fatigue. Field crews are tired, wet, distracted, and racing a clock. Fewer parts isn't just cheaper, it's kinder. Same tool everywhere isn't just simple, it's humane. Bolts every 6 inches isn't just strong, it's unforgettable. When a system is obvious, it is safer. When mistakes are hard to make, lives are harder to lose. Let's put the 60 days into scenes. Week 1, break the Nissan habit, shed the skeleton, trust the shell. Week 2, chase leaks, lift loads, bolt patterns stabilized. Week 3, shipping geometry, nesting tests, railcar fit checks, crate counts. Week 4, assembly choreography, the CB's mock. Build a bay, identify bottlenecks, cut the floor. Week 5, ventilation war condensation discovered, louvers sized, ridge vent detailed. Week 6, anchoring menu stake patterns, sleeper bolt templates, PSP tie-downs. At the end, the prototype team wasn't celebrating a building, they were shipping a process. Numbers anchor claims. The design modeling said the shell handled winds north of 100 miles per hour and carried snow loads 40 pounds per square foot for stateside use cases. Those are not combat promises, they're engineering targets. The war would throw worse, that's why the arch mattered. Under gust, it flexes like a bow and comes back. Under blast, it prefers to dent rather than shatter. Under rain, It sheds rather than soaks. Geometry buys you resilience, and resilience buys you time. And time is the currency of logistics. A barracks that takes weeks buys you 0 when the monsoon starts tonight. A kit that stands today buys you 8 hours of sleep, 12 of work, 24 of operations. That compound interest wins campaigns. Listen for the small choices that kept the big promise. Lap joints that overcover by 6 inches, so water must climb uphill to enter. Washers that deform just enough to seal without slicing the zinc. Holes placed off-crest, so the rib carries load while the valley sheds water. These are the places product thinking lives in the half-inch and the half-hour you don't notice until the storm tests it for you. None of this would have mattered if the parts of the machine hadn't meshed. Budox wrote requirements like mission orders and ran tests like interrogations. George A. Fuller Co. funneled shop pragmatism into drawings you could actually build. Strand Steel converted coils to ribs, dipped them in zinc, and learned to pack steel like origami. And the Seabees, God bless the Seabees, turned all of it into muscle memory and standard operating procedure. They're the reason one day wasn't a boast. It was Tuesday. So picture a strip of coral at dusk. A landing craft coughs up crates. 6 men carry panels like shields. 2 wrestle an end wall into place. Someone calls level. Someone else finds the bag of bolts. There's no concrete truck idling, no carpenter bench, no generator humming. There's a wrench, a mallet, and a page of drawings with more pictures than words. 8 hours later, there's a roof you can hear the rain on instead of feel it through your blanket. You've just manufactured survival. The physics held in the shop. The kit packed on the rail. The bolts ran easy in the hand. But designs don't win wars. Field performance does. Next, Guadalcanal's heat, the Aleutians cold, and a Philippines typhoon would grade the Quonset not on elegance, but on outcomes. Would the curve still slide the wind? Would the ring still hold under shock? Would the vents keep men dry when the night sweated inside the roof? The only way to know was to build and wait for the weather. Welcome to Guadalcanal, hot, wet, and angry. The first combat-deployed Quonsets come off landing craft under sporadic artillery. Crews don't have luxury, they have orders. End walls go up in a coconut grove, still black from the last fire. Panels overlap by 6 inches. Bolt, bolt, bolt. Louvers? Not yet. The kit is fresh from Rhode Island. The air is anything but. 12 hours later, 10 new structures stand at Henderson Field tool sheds, maintenance bays, bunks that don't drown. 3 days later, the island throws its pop quiz. A 500-pound bomb detonates 40 yards off a hut full of aviation mechanics. Canvas nearby tears like tissue. Palms fold. The Quonset flexes. Dirt and shrapnel rattle across corrugations. When the dust clears, the shell is dented, the seams hold, and the men inside are shaken, but alive. Blast is a liar. It promises to push you over, but mostly it tries to lift and unwrap. The continuous shell denies both. The hoop keeps neighbors in step. The anchors carry the hoop. The structure prefers denting to tearing. That is survivability, not immortality, engineered on purpose. Victory against explosions didn't win the comfort war. The jungle fought back with chemistry and biology. Within 2 weeks, any ungalvanized fastener wore a red scarf. Salt air ate cheap steel like sugar. Humidity grew art on every cool surface. Marines cut extra holes with tin snips. Doors stayed propped open all night because air had to move or men couldn't sleep. Field reports outranked drawings. The kit came home smarter. Every fastener galvanized. No exceptions. Louvers grew. Ridge vents went from footnote to standard. These weren't decoration. They were doctrine. The hut learned the jungle and evolved. Flip the globe. Now it's the Aleutians Dutch Harbor, ADAC. Temperatures plunge to 40 below. Wind writes horizontal rules across the snow. The same shell meets a different enemy. Brittle fracture and water that hides in your roof until night turns it to rain inside. Early panels cracked at bolt holes in deep cold. That's stress concentration plus metallurgy. Solution 1. Switch to cold-rolled steel with a friendlier grain for Arctic service. Solution 2. Add rubber gaskets under washers. Keep the seal flexible. Let joints move a little so the shell can breathe through gusts instead of tearing itself at its weakest circles. Heat invites condensation. Warm air meets cold steel. The dew point gets jealous, and water falls where you sleep. The fix wasn't hotter stoves. It was ventilation plus insulation. Run the louvers even in winter. Install batting against the shell so the inner surface stays warm enough to stop the nightly rain. Moisture management is the unglamorous half of survival. Operationally, Arctic crews learn to keep a trickle of air moving and to respect the ridge vent. Shut everything to save heat, and the roof makes a cloud for you. That lesson turned into standard winter SOP. Vent a little, heat steadily, insulate well. The curve will handle the wind. Your job is to handle the water you can't see. December 1944 Typhoon Cobra rips into the Philippines. This isn't a storm you watch through a window. It's one that measures your fastening patterns. On a coastal base with 43 Quonsets, 39 ride it out intact. 4 take repairable damage, bent panels, torn seams, but no total collapses. Engineering analysis afterward found the separating line wasn't a new geometry. It was old anchoring. The huts with proper ground attachment stakes set deep, cables tensioned, sleepers bolted, stayed planted. The few with improvisations rolled. The arch carries load, the ring shares it, the anchors close the circuit. Under typhoon rules, the weakest link writes the ending. If you ever doubt anchorage, remember this storm. It didn't prove Quonsets are invincible, it proved systems are honest. Build the full system and you get the promised curve and ring performance. Shortcut the ground and the sky will collect its tax. One more exam, Palermo, Sicily. A hut pressed into service as an ammunition depot takes a direct hit from an 88mm shell. That's a recipe for a crater and a memory. Instead, the arch shell channels the blast outward. The frame twists, panels deform, and the skin is shredded in places, but the structure doesn't pancake. EOD crews later note, a rectangular roof sitting on walls likely would have collapsed in a slab, trapping anyone nearby. The arch, acting as a continuous ring, gives the blast a path to leave. Blast physics are cruel to discontinuities. The Quonset had fewer. No beam to column joints to unzip, no roof to wall seam to pry. One shell, one ring, one set of dents. Damage? Yes. Catastrophic progressive collapse? No. Design doesn't promise miracles. It promises failure that you can walk away from. All this field data would have meant little without a repeatable way to build. The Seabees turned the Quonset from a great design into a great routine. A standard crew of 6 to 10 can stand a 20 by 48 in about a day site to shell. No concrete, no welding. Here's the choreography. Step 1. Site prep. Level just enough to avoid pooling. Cut vegetation. If gravel is available, spread a thin base crown slightly so water leaves the hut, not enters it. The best shelter earns nothing if the floor becomes a pond. Step 2. Anchors before walls. Stakes and guys on sand. Sleepers on coral. PSP, where you need an instant pad. Tension cables to spec, you want preload, not slack. Anchors now save roofs later.
Step 3 shows end walls first.
They index the shell
Two
and square
workers
the
lift
job.
and
Brace
position the
them lightly.
Quonset Hut end
They'll
walls,
carry little in the final
temporarily
state,
bracing
but
them
they
with
steer everything that
diagonal
follows.
supports.
Step 4. Run the shell. Overlap 6 inches, bolt every 6. Work symmetrically left, right, left, so the developing ring doesn't lean. Hand tools only, 1 wrench size across the job. That trainability was designed in on purpose. Step 5. Vent as you go. Ridge components bridge the crown without cutting the ring. End wall louvers go in on hinges, stout enough for typhoon duty. Sealants and tapes live where the manual says, not where you guess. There's a reason every hole and lap sits where it does. Step 6. Tie downs and test. Retorque bolts. Retention guys. Walk the perimeter and spray the laps if you have water to spare. Any drip you find on day 1 saves a night of misery in a storm. A trained demonstration crew once raised a hut in 4 hours and 17 minutes. Impressive, but that's a sprint on flat ground, with seasoned hands. What matters for war isn't the record, it's the routine. 5 or 6 huts a day, day after day, across islands. That's logistics you can sleep under. By 1943, the Quonset wasn't a frozen blueprint. It was a living spec. Guadalcanal taught corrosion and air. The Aleutians taught metallurgy and moisture. The Philippines taught humility about anchors. Palermo taught how an arch fails better. Each lesson became a line in a manual, a new part number, or a bigger louver. That's how you mass-produce survival, not with one perfect design, but with a design that learns faster than the weather changes. Because under every calculation and corrugation lives a simple outcome. Dry boots, warm hands, engines that start at dawn. A crew chief who can plan tomorrow because tonight's roof will be there in the morning. The Quonset didn't beat the war. It beat the weather long enough for people to fight the war. Field validation earned the one thing factories love: confidence. With proof in heat, cold, wind, and blast, production could scale without apology. Coils became corrugations. Corrugations became kits. Kits became roofs that outnumbered storms. Next, we head inside the machine. Corrugators, zinc kettles, flat-pack choreography, and the economics that turned a drawing into a housing system by the tens of thousands. Scale begins at a dock in Rhode Island. Quonset Point proves the idea: turn buildings into kits, turn kits into throughput. Within months, the Navy needs more huts than one base can dream of stamping out. The job spills inland into mills that once made grain bins and water tanks, and the line between construction and manufacture disappears on purpose. By 1942, Great Lakes Steel's Strand Steel Division comes off the bench. Their background is agricultural arched barns and ribbed panels, but the Navy's brief turns it into war work. Output accelerates, standardizes, multiplies. Tooling gets dedicated. Coil schedules get priority. Entire buildings inside the plants get renamed Hutline ABC. How much? Contemporary reporting puts Strand Steel's wartime total near 155,000 units, a number echoed in post-war articles, and the overall World War II build across all suppliers lands somewhere between 150 and 170,000 huts. That isn't a curiosity. That's national capacity applied to a shape. Production wasn't one monolith. It evolved by model. The early T-rib line, about 8,200, gives way to the redesigned shell, roughly 25,000. The workhorse becomes the 20 by 48 and 56, on the order of 120,000 between them. Warehouses stretch to 40 by 1 to 100, nearly 11,800. Different ribs, same ring. Different lengths, same logic. Standard plans lock the diversity into something crews can master once and repeat anywhere. If a kit says 20 by 48, the bolt pattern, louver package, and rib count are baked into the number. That's trainability, and it travels better than explanations. Start with a coil 4 feet wide, tons heavy. Feed it through corrugators that impose a rhythm, 2.67 inches on center, crest to crest. Corrugation work hardens the steel. The shape strengthens the sheet. Stiffen the metal before it ever meets weather. Punch holes where the manual says every 6 inches along the overlaps. Cut end profiles so panels nest like bowls. Nothing ad hoc, everything indexed. Then send the panels to a bath that matters more than paint ever could. Hot dip galvanizing at roughly 850 Fahrenheit forms a metallurgical bond. Zinc gives itself up first to corrosion, so steel doesn't have to. In salt air, that sacrifice buys decades. From there, the line turns steel into shipping geometry. 96 panels nest down to a 14-inch bundle. Add end walls, plywood pre-cut for doors and windows. Add a crate with every fastener, washer, and louver hinge in labeled bags, plus illustrated instructions for men who might speak different first languages but can read a picture. A complete hut sits on one standard 40-foot flat car. Westbound trains don't carry buildings, they carry capacity. On the docks, Liberty ships swallow 200 kits a voyage. 200 huts is 7,200 bunks, or a field hospital plus chow hall plus maintenance bays crane-loaded in an afternoon. This choreography looks simple because someone did the hard work. Agree on hole patterns, lock the wrench sizes, decide once how panels nest, commit to 1 crate per hut. The payoff shows up a month later on an island where the kit unpacks in the right order, and the last bolt you need is actually in the box. The brief said under $1,000. That was a target useful for focus, not a law of physics. Field reality pushed the bill higher. Hot dip galvanizing, larger louvers, better hardware, wartime inflation. A typical 20 by 48 mid-war comes in around $1,394 in materials. Assembly time lives in the same grown-up world. You'll hear numbers from 14 hours to 1 day to 60 man-hours. They aren't contradictions, they're contexts. A 6-man team, after a short orientation, put up the first prototype in 14 working hours. The Navy's manual standardizes around a 1-day goal for a crew of 6 to 10. Add site prep, anchor setting, and internal fit-out, and most units land between 48 and 60 man-hours of labor. Compare that to roughly 400 hours of skilled carpentry for a wooden barracks. Price is only half the ledger. Risk sits on the other half. A wooden barracks needs lumber on an atoll that has none, and carpenters on a schedule that doesn't exist. The Quonset needs a rail car, a hold in a cargo ship, and people with wrenches. Dollars decide budgets. Logistics decide wars. It's also honest to say the Quonset carries operating costs in weather. Insulation for cold, sound control for rain, corrosion checks on bolts. Those are consumables. But once you own the shell and the kit, the line between we can't build yet and we're inside collapses in a day. That's the cash flow of shelter. Factories didn't build huts, they manufactured survival. Corrugation isn't decoration, zinc isn't paint. A crate of labeled bolts is a promise that strangers can become a crew in an afternoon. When you send that promise by rail and by sea, you replace carpentry with choreography and hope with lead times. That sentence sits behind every number you've seen: 150,000+ kits, 200 per ship, 14 inches per bundle. It also sits behind the human outcomes: dry equipment, fewer sick calls, crews that start work at dawn because they slept. In the next act, all that capacity meets demand back home. Surplus huts turn into neighborhoods, classrooms, shops, and sanctuaries. The arch that learned war learns civilian life, and somehow refuses to retire. Steel in, shelter out. That was the equation. And for a few intense years, America solved it by the tens of thousands, then sent the answer to sea. When the shooting stopped, the scarcity didn't. Millions of Americans came home to a nation that could not build fast enough. Lumber was tight, crews were booked, babies arrived. The War Assets Administration faced a strange problem. The military had more shelters than it had wars, and the public had more need than it had roofs. Surplus Quonsets didn't trickle into civilian life, they flooded it. Municipalities leased whole blocks. Veterans formed co-ops. Universities carved out married student villages from rows of steel arches. The same geometry that beat typhoons beat the calendar and the rent. Los Angeles built an instant town called Roger Young Village, 750 families living under corrugated curves, with porches, gardens, and laundry lines strung between ribs. On campuses, vetvilles sprouted next to labs and libraries, rows of huts sliced into living rooms, bedrooms, and tiny kitchens. At the University of Iowa, a cluster called Quonset Park became a whole neighborhood for married students, where finals and first steps happened under the same arch. Why choose steel huts over stick-built? Because time is money, and shortage is real. A surplus Quonset bought for a fraction of new construction could be on footings and occupied in days. A conventional house needed materials the market couldn't supply and crews the calendar couldn't free. The math that solved Guadalcanal solved the GI Bill. And they weren't just homes. Churches put congregations under arches, while capital campaigns caught up. School districts facing the baby boom turned huts into classrooms by the thousands. On the prairie and the edge of town, farmers and mechanics discovered a business model. Clear span space with no columns, delivered as a kit for less than a couple months' rent elsewhere. Quonsets got so common that paint companies made products just for them. Sherwin-Williams sold Quan Coat, a finish formulated to grip galvanized ribs. When a product earns its own paint line, it's not a fad, it's a fixture. Decades passed. The huts stayed. You can still spot them on county roads. A farm shed here, a machine shop there, an ag spray hangar near a field strip. Colleges kept a few as storage. Cities converted them into public works barns. On some bases, wartime Quonsets outlived the officers who first signed their receiving papers. Back where the story began, Davisville Quonset Point houses the CB Museum and Memorial Park. Walk the grounds, and you can step into 7 original huts, preserved and staged, the ribs still carrying load like they did in '43. It's not nostalgia, it's evidence. Strand Steel ended its hut production in 1959, but the form refused to retire. The market picked up the silhouette arch buildings, Q-style, style made by a dozen manufacturers across the map. Materials improved, coatings got smarter, bolt kits got friendlier. The basic proposition didn't budge: a curve, some ribs, a crate, and a deadline you'd otherwise miss. Look at refugee housing units in today's camps. The materials differ: composite panels, snap-fit frames, but the playbook is old. Flat pack shipping, unskilled assembly, curved or stiffened skins, vents that fight condensation. If you've seen a Quonset manual, you recognize the choreography. After Hurricane Katrina, engineers mapped what fell and what didn't. Curves consistently outperformed boxes. You can brute force a wall, or you can invite the wind to leave. The physics didn't care what decade we were in. The tiny cabin movement stumbled, almost accidentally, into the same geometry. Arch roofs, ribbed skins, open spans. Marketed as sustainability, sold as lifestyle, anchored in wartime engineering. For rapid deployments, container expandable kits unfold like origami and lock into rigid shells. Helicopters sling them, crews click them. Inside an hour, there's light behind a door and a roof that won't argue with wind. If you sketch a Mars habitat, constraints rhyme with 1942. Cargo is precious, foundations are dubious, tools are limited, weather is mean in its own way. You end up circling the same answers: arched profiles, factory parts, flat pack shipping, assembly by small teams. We didn't invent that for space. We learned it in a hurry, under a different sky. That doesn't mean a Quonset would sit on Mars exactly as is. It means the logic that built 150,000 huts in months, not decades, still pays rent wherever many fast, cheap, durable is the problem. If you had to shelter a city in a week, what would you build? Would you fight the wind or invite it to leave? Would you wait for carpenters or ship a promise that strangers can assemble into safety? The Quonset answered once. The world keeps asking. Steel taught us a simple sentence: don't just build, manufacture. Post-war America used it to house families. Today, we use it to ride out storms and rebuild on Thursdays what Monday took. Tomorrow, different planet, same math. Before we roll credits, here are the core sources behind today's story short. Solid and checkable. U.S. Navy Bureau of Yards and Docks Manuals, Northern Design, 1944. Warehouse divided by 40 times 100, 1944. U.S. Navy Seabees Museum divided by NHHC Photo and Plan Archives. The New Yorker, March 16, 1946, Strand Steel Production Accounting. Fort Collins Research Summary Model Counts by Configuration. Nissan Basics, Wikipedia, and NHHC Overviews, used for foundational facts only. We trimmed citations on screen so the story could breathe. If you want to dig deeper, the pinned comment has direct image excerpts from the Navy manuals and a compact list of links. Names you saw today spelled right, said right. Research and scripting, archival prep, graphics, and voice team credits rolling now. Huge thanks to the Seabees community and curators who keep the paper trail alive. Pinned up top, 2 Navy manual diagrams, ridge vent and anchoring plate, full res. A one-screen source list with year and repository. Our timeline graphic you can screenshot for class or shop talk.